All right. So, as promised, here is the makeup lecture video for the lecture that was missed on September 28th. Because I want to keep the lecture video nice and compact and not bloviate too much, I'm going to kind of jump right in. One thing I will say is that I have emailed I'm sorry, rather, Dr. Kaltenberg has emailed Stata regarding the issues with downloading everything. I hope that we'll hear back from them by tomorrow. That way we can take care of this, and then you can kind of start next week having Stata. But if not, it's not a huge deal. It's watching me use Stata in preparation for when you are able to use it is fine as well. Also, if you really, really want to get some practice on Stata, if you go to the PACE virtual lab, so if you just Google PACE University Virtual Lab, you can actually access, I think, Stata 13 and also RStudio as well. But so if you just really need to do some Stata, you can do that in the meantime. But hopefully we'll have that cleared up. Just one of those things. I think that they probably, when they sent the username and password, they probably set the number of downloads too low for the number of licenses that we actually had. I think it's happened before, like in my experience, like I've had that happen before. I'm trying to remember, I can't, but I think it did. So it might be a common mistake. So regardless, we'll get it fixed. You'll get your Stata, and yeah. So you'll see me do several very basic things in Stata. We're going to keep it pretty basic today because we're just going to again start getting into some just basic statistics, but start talking about, like, what do they mean. A lot of statistics courses can get kind of caught up in sort of focusing on kind of like what the general population doesn't know about statistics, which is a lot of things. It's a lot of stuff, and it can become kind of a part that way. And I don't want it to go that way, right? I want to kind of focus on like what's actually sort of useful and that kind of stuff. So that's what we're going to focus on. We're going to focus on, okay, what do we need to know? So I would say that the stuff that we talk about in this lecture, and then the lecture we have on Tuesday, are really going to be focused on, like, what's the foundational stuff, like what's the stuff that you need to know. This is not stuff that you want to have kind of reference to. You want to, like, know what's going on. Now, that doesn't mean that you necessarily need to learn all the equations and all that stuff, although there's benefit to doing that as well, because then you don't have to necessarily go and look them up, but you want to understand the concepts. And sometimes you can understand an idea or a concept and not necessarily know exactly what the equation is that describes it. But as long as you know the idea, you can always look up the equation, and there you go. So what we've been talking about, we did some probability theory. Then we started talking about sort of the concept of like frequency statistics, and frequency statistics is at the heart of a lot of what we do in econometrics. And so that's why we spend a nice chunk of time talking about kind of frequency statistics, and had an interesting conversation regarding like bar charts and versus, histograms. We talk a little bit about probability distribution functions and cumulative distribution functions. And again, the purpose of all that stuff is that stuff underwrites, in a way, a lot of what we're going to be doing when we get to linear regression. So we'll be bringing that stuff back. So again, they're that nice little foundation. So what we're going to talk about in this lecture really is mostly about this concept of dispersion, or what we would say a lack of centrality. So dispersion roughly sort of relates to the extent to which the observations of a variable, the sample of a variable, is dispersed along the continuum that variable values take up. So, you can think about this. Sometimes we call it the spread of a variable. It's really just visually, you look at a histogram, which we have here. We have two different histograms, and the extent to which those histograms are dispersed versus show centrality is, of course, going to be a function of the underlying data itself, and not just the variables, but the sample of data, because sometimes we really want to distinguish between kind of population statistics versus sample statistics, because those are distinct ideas, and we'll keep kind of talking about that distinction as we get into linear regression, because that distinction is actually quite important. And I would say it's something that students often don't pay as much attention to for fairly obvious reasons. It doesn't seem very helpful, but it's one of those things that I think holds a surprisingly a lot of value to the concept there. So these are, two distinct histograms, and they look in a sense kind of fairly similar here. But then if we, looked at different samples, so here we can see that the orange sample is a lot more dispersed relative to the blue sample, for example, but these two have very similar means. So the means are going to be quite close because, again, remember, when you look at histograms, envision that probability distribution function, that normalized probability distribution function, and where that function peaks is where the theoretical mean is, or I'm sorry, where the mean is. And so if we look at these two particular graphs, we can see that these graphs have figures have essentially the same mean, but the dispersion of the data is much different, with orange having a much larger dispersion than blue. This has so many potential sort of consequences for the statistics that are computed from data. There's just, first off, the sort of important information of how the data is dispersed and to what extent it is dispersed, and then how it's dispersed, right? Because you have like normal distribution, but then you have sometimes data which looks almost like a non kind of normal distribution. Let me give you an example. So one of the things that we can do in Stata is we can do something called a Monte Carlo simulation. And I'll be using Monte Carlo simulations a lot over the next few weeks because it's just a great way to learn statistical analysis. So the idea behind a Monte Carlo simulation, let me get the do file editor here, is that we actually create simulated data. And because we simulate the data, we know what's going on with it. And then we can sort of you can analyze the data armed with the information that we know what's going on. And that'll make more sense in just a moment. But the first thing we do to start a Monte Carlo simulation is we set what's called the seed. So we say set seed, and then just any random number. It doesn't really matter what it is. Right? It could be anything. Basically, what the seed is that there's going to be a random number generator that produces our variables, and the seed is kind of like the beginning of that. So if you use a different seed, you get different random numbers generated from any given Monte Carlo simulation. Let's set the observations, the number of actual data points that we're going to produce. Let's set that at like 10,000. Just let's assume we have a nice big data set. Okay. So now what we're going to do is we're going to create a variable, and we're going to give that variable a specifically normally distributed value, or sets of values, I should say. So we'll call this a variable x. So generate x equal our normal. So this is going to create a random normal, so normally distributed variable. We'll just give this a mean of 10, and then the second value is the standard deviation. So we'll go 2.5, just something very basic like that. And then I'm going to create another variable, but this variable is going to have, it's going to be distributed sort of differently. And so let's do gen z equals r beta. And then let me just look up what's the wrong notepad. There it is. Just got two. All right. All right. So the R beta is going to produce what is referred to as a beta distributed random variable, and I'll show it to you, and then I'll explain to you what it is. So what we're going to do here is we're then going to do a hist of x, and we have 10,000 observations. So let's set the bin to 100. And then we'll look at a hist of z, also with the bin set to 100. All right, and then I'm just going to run all of this code, and I'm actually going to run it all the way to hx, or histogram for x, and it'll do all this, and then it'll produce the histogram, and then we can do the one for z. All right. So we do that, and as we expected, or as we told Stata, it produced a normally distributed variable with a mean of 10 and a standard deviation of 2.5. We'll talk about standard deviation, how to calculate it, and everything here in just a few moments. All right, but here we go. This is our 10,000 observations of a randomly generated variable with a mean of 10 and a standard deviation of 2.5. Now we're going to look at a beta distributed variable. Now, the beta distributed variable here, these refer to basically the extent to which the distribution goes in a particular direction. So you'll see what I mean in just a moment. So let's actually do this. So let's gen, and then we'll do like y equals beta. And then let's do like 5 and 3. That way you'll see what it means. That's the best way to kind of understand it. So let's first look at the distribution of z. All right. So when you look at z here, so the idea behind like beta distributions is that typically, we would refer to this as like a very skewed distribution, right? But it's so skewed that it sort of very much borders on non-normal distribution. Of course, the big thing with non-normal distribution is the more non-normal your data is distributed, the less informative the mean value is. That's really important for us because when we get to linear regression, most of what we are dealing with is means. And so if your data if the distribution of your data renders your mean computationally less valuable, that's an issue. Right now, what's interesting about this is that we actually later on, we'll talk a little bit about this next week, but we can actually take data that is not distributed the way we need it to be. We can make it distributed the way that we need it to be, and very often not lose any statistical value, which maybe doesn't make a lot of sense to you now, but we'll explain that a little bit later. So now let's do the second one, the y variable, and then we'll do a hist of that. Let me just add that here. Hist y 100. So this one, you'll see that the first factor is 5 and the second factor is 3, so much closer together. All right, and let's do. All right. So as you can see, the idea behind like the beta distribution is that you can skew your data one way or another. So the farther away those two values are, the more skew you have. And so when I set the first value to 10 and the second value to 2, it gives me a big rightward skew of my data. But then as I converge those two numbers, you can see the data looks much more normally distributed. Distributions of data become an extremely prominent part of the modern analysis of econometric methods. What I mean by that is that there's like econometrics. That's like using econometric methods to perform statistical analysis. And then there's like applied econometrics, which is that you're studying econometrics, not the things that you're using econometrics to study, but you're actually studying econometrics. And one of the things that we've learned from that research is that distributions and sample distribution are super important. I mean, they're like, and so the field has really gravitated to focus on that. And so a lot of like the newer kind of cutting edge stuff has to do with assumptions as well as the realities of distributions. So regardless, you now know in Stata how to create a random variable, how to create a random variable which is normally distributed, and also how to create a random variable which is sort of normally distributed but is like very skewed. Just to kind of drive the point home, let's do gen q equals r beta, and then let's do like 1 and 100. And then we will hist u. Run that. There you go, right? Now, this is not, you would not at all call this normally distributed, right? In fact, we will later on refer to these types of distributions as chi-squared or chi-squared distributions. So that's the thing. If you take your r beta, your beta distributions and you push them towards the extremes, they actually become non-normal and really end up becoming like chi-square distributions. And so that's what we're looking at here. So we'll talk more about that later on. But there are a lot of data that actually has distribution. There's, I think, a sense from a lot of like kids who, when they first take elementary statistics, because everything you do is normally distributed because that's the simplest thing to work with. They're sort of, oh, okay, data everywhere is normally distributed, and that's just obviously not the case. And so this stuff is very important to us. So not only is just the extent to which we have dispersion, but how is the data dispersed? And to what extent does the nature of that dispersion, both the size as well as the type of dispersion, to what extent does that matter? To what extent does that affect our analysis? And of course, we're talking about it because it's fairly profound. Like I said, at the root of this discussion is our use, our conventional use of the population mean, and then of course, ultimately what we'll refer to as the sample mean. So the population mean looks from, it's a very basic mean, the sum of all values of a particular variable in the population divided by a count of all variables in that population, right? So it's the classic mean. We're pulling no punches here, right? But it's really important that you don't lose sight of the fact that the central component of most forms of regression analysis is simply the computation of a sample mean, which we believe in large enough samples converges to the population mean, right? I mean, that's kind of the idea. A lot of this goes back to that conversation we had about expected values of data, like the expected value of some variable X ultimately in probability theory ends up being the mean of X. And then that refers to the population mean. When we get to actual like regression analysis, we're using samples of population. So you have a sample mean. But of course, statistical theory says that in large enough samples, the sample mean is going to converge to the population mean. So the sample mean is supposed to represent the population mean. And oftentimes we know under what conditions that will not be true. Maybe we have low sample sizes, like that's the most obvious way that the mean will not be very representative. But there's a whole host of other reasons, and we'll certainly spend a lot of time talking about those. So for the arithmetic mean to be meaningful, the data must be measured at the interval or ratio level, so temperatures, ages, or incomes. It's important to point out that the mean always exists, like there's always a mean value, and it's always unique. There's always a unique mean value for any particular population variable in question. And then one of the other things to keep in mind related to linear regression is that so much of what we're going to talk about refers to the use of this concept called deviation. So we can measure deviation in a lot of different ways. The typical way that we measure deviation is we pull an individual observation of a variable and we compare it to its mean, in this case, the population mean. So imagine that we have some variable X. It could be like height, people's height, and I pull a random height from it, and then I compare it to its mean. We refer to that as a deviation. And the deviation, the sum aggregate of deviation in a population mean is going to be zero, right? Because if you get every single person, you get the population, you have their heights. When you add up all of their deviations, you're going to get an equal amount above and below that mean. And so therefore, you're going to get a zero. That's going to come up later. It's going to come up in a way that you probably don't expect. And the way it comes up is it has to do with standard errors in linear regressions. And basically the principle ends up being in order for an error term to be truly what we call white noise or having no deterministic effect on some causal relationship, we need the deviations above and below the fitted line to equal zero. So this actually comes back in ways that is I think, somewhat surprising, or at least was surprising to me. Of course, what we care about, what we mostly work with, is the sample mean. And the sample mean is just the same idea as the mean, except we understand that with a sample, we have a sample mean, which is potentially distinct from a population mean. The way that we denote means is almost always with a bar above a variable. This is true in Stock and Watson as well. So whenever you see like X bar, that refers to the mean value of X. And so you can see an equation here, classic definition of a sample mean. X bar is equal to an aggregate or summation of all the values of X divided by the sample size of X. Pretty straightforward. Um, One of the things that students often show up to Echo 240 in sort of research methods courses is they're like heavily concerned about like outliers and things like that. I think I've already mentioned this, but actually in modern era sort of econometric analysis, we're much less concerned about outliers. And so ultimately they end up not being a fairly important part of most of our discussions, except for it sometimes becomes an active component of your research methodology, whether you remove outliers or whether you do not. And so it's an important conversation. Don't get me wrong, but we sort of evolved a little bit. Back in the day, it was always you got to remove outliers because outliers make your data not representative, right? In a way, the argument was that if we compare the sample mean to the population mean by removing the outliers, we're taking the sample mean and we're moving it closer to the population mean. We now know that's not true. In fact, leaving the outliers in because the outliers are part of the population, in fact, makes the sample more likely to be closer to the population as long as the sample size is high enough. Right now, if you have a very low sample size and you have outliers, that's a huge problem. So the problem of outliers is solved like the problem of most problems in statistics is with sample size. The median obviously is a very common measure when we're talking about economic values. So, for example, we don't normally talk about the mean income in the United States. We most often talk about the median income in the United States, and the question becomes why. Like, why in the context of income do we talk about median versus, say, in the context of height, we talk about usually like the mean. And it's because of the distribution, right? That's why we talk about them in different ways. So if we go back to the distributions here that we were just looking at, let's just do the normal distribution here for X. Okay, so here the median value of X is going to be fairly close to the average, right? Because again, remember what median is, right? I think this is a good, nice definition to keep in mind. It's the midpoint of values after they have been ordered from the minimum to the maximum value. So it's that literal midpoint of the dispersion of your data. Now, if your data are completely normally distributed, then the midpoint is also the mean. So there are certain conditions, of course, where the median equals the mean, although with any sort of unequal dispersion on either side to the right or the left, the median is going to be distinct, and it's typically distinct from the mean. So here, the mean and the median, of course, are going to be very close together. Whereas if you have a distribution like, the heavily skewed one here, the mean and the median oftentimes give us different information because the underlying distributions from which those values were calculated are distinct themselves. So the use of mean and median, even though we may not frame it this way, is because of distribution. That's why they use those distinct measures. Now, let's take a second to step back and go, remember, a mean is an estimator, okay? A median is an estimator. So when we talk about estimators, remember when we're talking about sort of different terminology and statistics, right? When you describe a statistic, there's a statistics, um, you know, like random pull of a particular variable could be an estimator, right? Now, is it a good estimator? So in other words, I'm saying, like, say you have a sample and you just randomly pull a value out of that sample. and that forms your expectation. Okay, is that a good estimator for that expectation? Probably not, right? That no, right? Whereas if you have a normally distributed data and you have a mean, now the mean is a good estimator for which value you have the highest probability of pulling if you pull it random, right? You see what I'm saying? And the median becomes a good estimator for whatever value within a given distribution that you want to know where the midpoint is, right? And think about that from the context of like the midpoint of data. Why is that important? Well, in the context of like incomes, for example, we think the median is more representative of an estimator of the typical income in America. So because the distribution of incomes are what they are, which is pretty similar to what you see here, we believe the median is a far more reliable estimator of the expected income. Whereas in normally distributed data, the best estimator of the expected value of a given variable is going to be its mean. So even though you've been using averages and you've known about medians for a long time, you probably not refer to them as estimators. And what we mean by estimators is they estimate the value of information, right? So a mean is important insofar as it provides us information that is valuable. And there are things that make means less informationally valuable and things that make medians more, and vice versa. So it's important for us to know when that is. And more so than that, it becomes important for us to know how that affects things like linear regression later on. And it absolutely does. You can, in fact, do linear regression using medians instead of means. There's actually nothing wrong with that. But means become the simplest way to kind of do linear regression. So that's mostly what we do. So that's why we spend so much time talking about means. Okay. That's what I was just saying. If you look at like income, U.S. income over the last 40 or so years, you'll see that the mean income is much higher than the median income. And the reason, of course, is going back to the distribution that looks like this, is that the median is going to be closer to the bottom because we're ordering the median relative to its, we're like, there's a lot more people who are at the low end of the income scale. So as you order those values, the midpoint becomes much closer to the bottom. Because when you order all of these values, there's a lot more values at the bottom. And so the midpoint happens much further to the bottom, whereas the mean is going to happen somewhere up here because you have these like extremely high values that are pulling the mean up. And so the distributionally, what we are often arguing when we use the median versus the mean is we're saying that the mean overrepresents high incomes. And therefore, if we use mean to represent like expected income in America, then we're setting expectations that are higher than probably reality, because much fewer people have the mean income than have the median income. So the median income becomes a better estimator for our expectation about what a random pool of income would be from society.